All right, so Screencast, Unit 2, Lesson 4. Really critical topic. I could describe it as writing what are called Lewis structures. But what a Lewis structure is it just shows you where all of the electrons are in a molecule, which ones are being shared, which ones are not being shared. And this is going to help us determine the shape and the behavior of molecules in our world. All right, so anyway, this is just going to be our screencast. That'll be my name, Screencast. All right, so let's just get straight to it. A Lewis structure is based off of localized electron theory. That means that electrons are local to individual atoms, and all the valence electrons are going to be depicted as dots. We've seen that already. Dots in between atoms are shared. Remember, a shared pair of electrons is a bond, and we typically show it with a line. And dots that are not in between atoms are unshared or unbonded electrons. So if you take a look at this molecule right here, HCl, I could write it as HCl, showing my shared pair of electrons as a bond. Now, our hybridization here around this chlorine would be sp3, just to review some things. This would be a sigma bond between the hydrogen and chlorine. Okay? All right. Now, how many shared pairs are present in this molecule? Only one. Just this pair is shared. How many unshared pairs? 1, 2, 3. To show you how this molecule was built in the first place, how many valence electrons does hydrogen have? 1. This is using your periodic table. Chlorine has 7. How many total valence electrons are in this molecule shown with our dots? 1, 2, 3, 4, 5, 6, 7, 8. Notice that is exactly the same as the total of the number of valence electrons. So there's a rule right there for writing Lewis structures. Your Lewis structure must have the same number of electrons as you would if you summed all of the valence electrons of your atoms. And that makes sense. You're going to have the same amount of electrons involved in bonding as you would valence electrons available. So it would be reasonable to assume the number of dots must be equal to the total number of, you know the answer to this now, valence electrons of all the atoms in the structure. I've already showed you that a shared pair is often described as a line. Now let's look at some criteria that have to be met in order for a Lewis structure to be considered valid. We've already talked about criteria 1. You have to have the same number of electrons in the molecule as there are valence electrons from the atoms. Criteria 2, atoms form bonds to get a full energy level. We call that often a noble gas configuration because noble gases have a full S and P. Now there's some exceptions to the rule. For hydrogen and helium, that's just going to be 2 electrons because that's a full energy level for them. For most other atoms, they're going to want a full S and P. That's 2 from the S, 6 from the P, which is the octet rule. Full S and P means a total of 8. We already know this. All right. As I said, most atoms obey the rule, but there are some exceptions. Like I mentioned with hydrogen, all he'll ever have is 2 because that's a full S. He does not have a P. Beryllium will only ever have 4 electrons. Beryllium only has 2 valence electrons. So all it could ever form, normally those 2 valences would be in the 2s. All beryllium can ever do is hybridize its S and P and put an electron in each. So all beryllium could ever be is sp hybridized, which means 2 orbitals. That means 2 pairs of electrons, which equals 4 electrons. So beryllium will never have more than 4 around it. Just doesn't have enough electrons. Boron will be 6 electrons. Same problem as beryllium. It doesn't have enough. If you were to write the electron configuration for boron, it would finish with helium and then 2s2, 2p1. So if he were to hybridize his s's and his p's, the max he could hybridize would be 1s and 2 of the p's in order to put an electron in each. He only has 3 valence electrons. So he can't do sp3 hybridization. That would be 4 orbitals, and he doesn't have enough electrons to spread out to form bonds that way. All right, so boron will only get 6. Beryllium 4, hydrogen 2. So these are exceptions. Memorize them. Some elements in period 3 or below can sometimes exceed the octet rule, meaning they'll have more electrons around them. And that is because they have access to the d orbital. And so anybody in period 3 or below. And I mentioned that here. But remember, the first energy level with a d orbital is period 3. So some examples would be sulfur, iodine, phosphorus, krypton. All of these might have more than 8. They could have 10 electrons around them, or even 12. Now, criteria 3, it's not going to make any sense to you because you haven't learned how to calculate it yet. But atoms will have what's called a formal charge close to 0. But if they can't be 0, if someone's going to have a negative charge, it'll be on the more electronegative atom. So these are the 3 criteria that must be met for every Lewis structure. Classic example of stuff you'd want to put in your study guide. All right, let's take a look at this now. How many valence electrons or dots will be in these Lewis structures? So you just count your valence electrons. Nitrogen has 5. Hydrogen each has 1. Now this is a 4 here, even if you can't see it. So there'd be 4 times 1, which is 4. So this would have 9 valence electrons. If this was NH3, that would be 5, and 1 each would be 3, so that would be 8. How about here? NH4 plus. Well, NH4 would have 9. The fact that it's carrying a +1 charge means it lost 1. So this would only have 8 electrons. I know it's hard to see. This is CO3, 2 minus. Carbon gives you 4 valence. Each oxygen is 6. 6 times 3 is 18. That's 22. But it's carrying a 2 minus charge, which means this would have 24 valence electrons. It must have gained 2. Water, 1 for each hydrogen times 2 is 2. 6 for oxygen, that's 8. Notice how many times we bump into that. 8, 8, 8. Or a multiple of 8, 24. Let's check this out. So 1 times 2 is 2. Sulfur gives us 6. 6 times 4 is 24. 24 and 6 is 30. This is 32. Again, another multiple of 8. Atoms want to have 8 electrons. Now that won't always be true, and you'll see here in a minute. This would be 8. And here's one that's not going to be a multiple of 8. Each oxygen has 6 times 2. That's 12 valence electrons. That tells you that there's going to be pi bonding in there. Carbon dioxide, 4. 6 times 2 is 12. 4 and 12 makes 16. So that tells you there's going to be pi bonding in there. Boy, I can't read it. It should be HCO3 minus. So to count them up, you'd have, 1 here, 4 here, 6 times 3 for the oxygens is 18. 5 and 8 is 23, and it gained an extra, so 24, a multiple of 8. Boy, these lines are just in the wrong spots. I'm going to say that this is SO2, 6, 2 oxygens is 6 times 2, which is 12, so that would be 18. This is going to be PCl5, 5 for phosphorus. If you look on the periodic table, chlorine has 7 valence. Times 5 is 35, which is 40, another multiple of 8. And let's say this is XeF2. That would be 8. Fluorine is 7. 7 times 2 is 14. 14 and 8 makes 22. All right, summarize briefly in your own words what criteria must be met for a Lewis structure to be accurate. You're getting those criteria from here, so that should be pretty easy. What are 3 elements that typically have less than 8 electrons when bonded in a molecule? That's just a review question. Check it out from criteria 2. What minimum period must be an element in? Again, it's found on the first side, so check that out. Let's go to number 11. Explain why the Lewis structure below for water is valid in terms of the first 2 criteria. Well, criteria 1 is it's got to have the same number of electrons as there are valence. Oxygen gives us 6 valence. Each hydrogen gives us 1. 6 plus 2 is 8. So there ought to be 8 in the structure. 2, 4, 6, 8. There are. So I'm going to put same number of electrons as there are valence electrons. Now, criteria 2 is that the atoms obey their octet rule, or more generally, get a noble gas configuration. For hydrogen, all he ever wants is 2, and that's how many he's sharing, 2, so he is good. This hydrogen, all he ever wants is 2, all he's sharing is 2, so he is good. Now, what about the oxygen here in the middle? He is going to obey the octet rule. He wants a full S&P, which would be 8. 2, 4, 6, 8. Yes. So all atoms have a noble gas configuration, which I'll just abbreviate as NGC. Now let's get to number 12 and explain why this Lewis structure is invalid. And let's look at our first criteria, which is valence electrons. Carbon gives us 4. Each oxygen gives us 6. There's 2 of them. So 4 and 12 makes 16. Now, if you examine our carbon here, this is for criteria 2. Well, no, let's verify criteria 1. How many valence are in here? 2, 4, 6, 8, 10, 12, 14, 16. So this meets criteria 1, but it doesn't meet criteria 2, which is that each element has a noble gas configuration. This carbon has 2, 4, 6, this oxygen has 2, 4, 6, 8. He's happy, but the carbon in the middle only has 2, 4. That's not an octet. All right, so carbon does not have an octet. So this is not a valid description of where the electrons are in carbon dioxide. To discuss our third criteria for drawing a Lewis structure, we have to consider a concept known as formal charge. And I'm going to show you how to calculate that now. Formal charge can be understood to be the comparison of the number of valence electrons an atom normally has when he's by himself compared to the valence electrons it owns and shares when it's bonded. So it's a comparison of your electron count when you're by yourself and then your electron count when you are bonded to things. Here's an equation. Memorize it. Put it on a flashcard. To find the formal charge of an atom, you take your valence electrons that atom would have minus the unshared electrons minus the shared electrons divided by 2. So you just got to do it in order to figure it out. Oxygen, look on your periodic table. He has 6 valence electrons. Minus how many unshared electrons does it have? 1, 2, 3, 4. Minus how many shared electrons does it have? 2 and 2 is 4. Do your arithmetic. 6 minus 4 is 2. Minus 4 divided by 2 is 2. So 2 minus 2 is 0. That is a highly desirable formal charge, and that means that this satisfies criteria 3. Hydrogen has 1 valence, minus unshared, there are none, so 0, minus the shared, which would be 2, so 1 minus 1 is also 0. So since these formal charges are both 0, that is an indicator that this Lewis structure meets criteria 3, is the one that deals with formal charges. I've got enough time here to do one more example before I got to go teach the next block. But let's take a look at example 2. Find the formal charges on each atom in the bad Lewis structure for CO2. We already know that it does not obey criteria 2, which is that the carbon would have a noble gas configuration. But it's also going to give you some very bad formal charges. Carbon has 4 valence, we know that from the periodic table, minus no unshared, so 0, minus 4 shared, 2 and 2 is 4. 4 minus 2 gives you a plus 2 formal charge, and we want that to be 0, so plus 2 is not desirable. Oxygen's also going to have a problem. Oxygen has 6 valence electrons, but in both situations in this molecule, it has 2, 4, 6 unbonded minus 2 bonded. So 6 minus 6 is already 0, minus 1 is minus 1. So neither of these are 0. So since neither of these formal charges are equal to 0, it does not meet criteria 3. But at least the negative formal charge is on the more electronegative atom. You see, oxygen has a higher electronegativity than carbon, so the electrons are going to be pulled this way. So the fact that oxygen has a -1 charge, that's not all too bad. But as you're going to see, there's a way to draw this Lewis structure better so that all of your formal charges are 0. Explain why oxygen is more electronegative than carbon is. Well, you locate them on the chart. Oxygen's here, carbon would be here, nitrogen between. Same shielding, oxygen has an extra proton, so he pulls tighter and gives a higher electronegativity. All right, so I'm going to come back to the next screencast, and we'll examine why this is a good Lewis structure in example 3 for carbon dioxide.